Yeah, welcome everyone for cloud computing and big data to the second part of today, which is really a practical lecture with some demonstrations about Python, about Jupyter, but then also learning a little bit step by step the difference between cloud environments and essentially then also the environments you have on your local desktop. Basically here we talk about maybe Anaconda that you can nicely use on your local laptop, but then once you move to the cloud, it's a much complexer setup usually. But still, Python in a way doesn't change so much. Of course, we have libraries to be imported, and this should be now a little bit the idea, basically, that we do a couple of examples here. Or for all of those that are not familiar for Python, for those that know already Python, maybe a bit boring, but still at least understanding the difference between local and then also remote cloud systems is important. And we have also some ideas already in data sciences, understanding data exploration tasks, which is quite interesting as examples. So whenever you work with this, I think an important key consideration is to avoid confusion is mostly this. The URI is very important because it tells you also that certain packages are not available, because when you use a cloud, you will see not all of that what Anaconda is providing is just simply provided in the cloud. And also when you move from AWS back to MS Azure or the vice versa, or then also use Google Colab, you will see there different versions of Python libraries deployed. For instance, TensorFlow was very popular recently because some had TensorFlow 1, others were already at TensorFlow 2. So these are, let's say, common problems where even the simplest things of just thinking exactly about this, which seems now incredibly trivial to you, mean a lot, especially if you work with different clouds in parallel. So this is a key consideration, and it's how you very quickly always can directly see if you work local or in the cloud, right? That's one of the ideas. Now, when you think about basic variables and loops, when we do this here now in the basic examples, I already started with this a little bit. So checking here a little bit the script, what I have here to show you all. The idea is, of course, that you see a little bit in the overview here that something is running. You have here a green indicator that it's already running. That means the notebook is really active. It has a kernel here that is used. Basically, the kernel is idle still. It doesn't do anything, of course, because we don't make it work here. And we already said that these numbers in a way matter very much. You can basically restart the kernel. That is something what I would recommend to you also when you work with the assignments and you, let's say, still modify maybe here and there small pieces. As I said, you don't need to program everything, but here and there needs to be a modification done. So still think about that these should be consecutive executed, because there are some, let's say, traps when you do this. Here we see that's basically very simple with a couple of lines, not even to include any library. You can have this nice output here, a combination of strings and of numbers. You can have essentially here and just work with strings, which is also, if you think about C, those that are programmed in C already a very, very far away. You have to do an array of chars and things like that to get a string. So it's not that easy, but here you see everything in Python is quite nicely. And even for loops are relatively simple, which you see here. And of course, important is here a little bit the indent. For those that worked in Python know that already. So here it's particularly important to have this, for instance, so to print everyone in X inside the loop, which is all of our countries that we have essentially at one point in the loop. So very, let's say, straightforward programming and really readable programming, which is, of course, also one of the things why Python is so attractive. And you see with Shift Enter, we always can go through the different cells and also have if clauses like a normal programming language, what you would expect. No big difference here. So here we break then after we come to Iceland, saying also welcome to the University of Iceland as an example here. And yeah, we can, of course, modify that here. So basically saying do 5 by 5 as an example. But of course, this would not change the result, right? So this is basically something what you also have to then really put in the numbers. I think those who are programming a lot know that the one is just a string for the output. The other one is just really doing the computing. So nice combination, very simple material. I think the restarting of the kernel, however, is very good to realize and also a clear way of programming. usually also in the cloud. You will see that once you have lots of different code, on which is, for instance, a complete deep learning code that we will use in the assignments, there's just not 4 of those. You have a very long script to execute in a stepwise fashion. Or actually next week, when we start with MS Asia, logistic regression, still there's data preparation, there's certain elements. And then when you don't have this in the consecutive order, several things could actually then fail in the idea. And this is what I wanted to show a little bit here as an example for you, so that you understand what I mean. When you think about you execute one, you know that we have here defined, for instance, the languages, and that was fine. And basically, when I now would not have defined this here, let's say we remove this just, and basically we have this here low, and I work here and code here, you know, and then the third, I defined the languages. I go a little bit up and can reuse the languages, and all looks nice, right? But if you know from the consecutive, you know, view, and I mean, many of you know that, I just repeat that here for the online audience and for the YouTubers, essentially you come to the problem now that essentially there's no languages defined. Suddenly it was code, it was working, and suddenly the languages actually are really not before defined. And this is a typical error that you do in deep learning, in coding in these environments, because you have many different of those. And you actually are, of course, not really always doing consecutive, you know, honestly debugging here and always starting from the top. So you would always reiterate and maybe do this and then change a little bit. Welcome to the, or welcome to Iceland, something like this. You change the code and things like that, but you never really start from the top again. And that's how these trouble sometimes can happen. So before you send me emails for the assignments of having errors, please think about starting always consecutive, right? Again, I know it sounds trivial, but it really helps a lot. And the test of time really says that this is actually something which is important. And where many of the errors are actually also for us as really experienced, maybe data scientists, we have the same trouble again and again of it not doing it properly, and then, you know, ending up debugging something but we shouldn't debug so much. Good. I think this is more or less self-explained. The official syntax and the examples, I also put you on the slides here, not to take much more time of you from this, which is, let's say, really basic material. The scripts will be available also in the canvas if you want to play around with them. Of course, now working a little bit with vectors is with Numpy very convenient. Also there are, let's say, some hookups where you usually come into conflict when you, for instance, use it with TensorFlow or other, let's say, more sophisticated libraries. I just provide some examples where usually arrays exist, or, you know, problems when you use arrays with vectors and things like that. And I prepared here one. But before we go in this way, think about also, usually it's very good to just close these properly. Things like close and halt. So then you see also the green disappears, it's not anymore running. This gets incredibly important in the cloud, because think about it, in the cloud, you pay for everything which is running. We'll come to this, right? And a GPU, for instance, costs $24 an hour. So if you're in a startup and you just keep it running and you log out, it still keeps running in the cloud, right? So, and we will make some points with it. That's why it's very important to really understand to use the software properly, stop the kernel from running, because then also the charging in the cloud stops. On your laptop, it's yours. So it's your problem, right? But in the cloud, there are lots of different things. And we come to this in the different lectures. Basically, also happening in the assignments that some people not really properly log off and all the educational credits are gone. Right, so it happens because basically the cloud keeps on working all the time. Now, thinking about vectors, also there, I think most of you have worked with vectors and arrays, so I spare you the introduction. We said Numpy is a very important package. You see, Numpy is not a default, so when we talk here, NP, of course, it's not there, so the import is important, while of course you can play around with the name if you like. You can, of course, name it differently. I think the community often is using NP, though, as a kind of de facto standard for naming it that way for readability. But this is something what you can do basically as you please. Now again, indifferent therefore, however, thinking about vectors versus arrays, you can maybe see this one here, where this looks pretty much like a vector, but isn't, right? And now when you have a code from Python, which is basically thinking about a vector and requires a vector, would basically spill out an error, which is very hard to see, because essentially this is just, let's say, 5 random numbers, more or less in a set, because it has really not a proper dimension to it, like a vector would have, like a 5.1, right? Or 5 times 1. So when you work with vectors in TensorFlow and these tools, it's important that these little things matter. Here, for instance, is the hint that always this 2 bracket shows you a proper, let's say, vector. And the same, of course, goes for matrices. But here it's very, let's say, with one look, you maybe can overlook it. The random numbers, of course, are both there, but here it's really talking about a real vector, and this is more like a vector in an array fashion. And this is, let's say, typical hiccups as well when you work with some of those. However, you have lots of flexibility there. You can move one into the other and things like that. Maybe from the basic setup, I see some people get maybe also already asleep that have been working already here with vectors and Numpy and things like that. I just put an emphasis on those things which, you know, are maybe important here in the course. Again, if you don't know Python and so on, please and maybe look around. I think there are lots of Google resources around it. You will find incredibly lot of tutorials around Jupyter notebooks and things like that. So that should be a problem. Right, yeah, I think one of the things I wanted to say is the case sensitivity. That is, of course, also something to consider, especially if you work maybe with many different libraries. Goes without saying that if you do this, it's also not viewable. So there is some certain sense of sensitivity in terms of the cases, especially when you think about, let's say, all the different libraries which may exist and so on. So it's also important. And sometimes I get questions around that as well. This could be also relating to some artifacts. If you copy and paste code from a PDF, for instance, sometimes you see strange things behind here. So they are not visible for you, but there would be, it's hard to demonstrate this, but essentially being something which is not visible, but there's still characters and could make an error also in the Jupyter notebooks. But some of you know that maybe from general copy and paste and so forth. Good, yeah, so the little things matters, we had that. Matrices, I think that's just a short extension also here. Think about the cloud again, getting into the modus operandi, close and hold the kernel, right? So even if you do it now on our laptop, it gets you in the habit of really stopping this. So then matrices is just a very tiny example before we get to much more interesting examples. Again, we use Numpy here. But the point is, again, using maybe different ways of how you basically create here a matrix in different dimensions. You can create it out of an array yourself manually, but also use, of course, a random operator that we had just now. Here's also no surprise having the vector before, because essentially it's nothing else than having a vector. It's just a 1 times 5 matrix, so to speak. And of course, with 2.5, you then add the matrix, which is just an extension to the vector. So all of that is more or less simple stuff. So I think we can go on basically with this. And I try to make basically the similar things I demonstrate for you here also into the slides with some comments, right? For instance, here the typical problems of case sensitivity, the difference between an array and a vector is important and things like that. But let's move to the cloud a little bit, just as an example again. What else could you do? And when we start to use a cloud, maybe for more sophisticated things, one of the things would be what we also use in the course is really then data exploration with machine learning. Usually you have to have an understanding what data you have before you do machine learning. You do feature extraction, you do feature selection, something we call basically a data exploration and data preparation phase before you do the actual modeling in machine learning. And you have seen this example already in the beginning, in the prologue, and also in my first part. Now, the idea would be that we basically create a system in the next couple of lectures that would identify those different images, right? So it would say, is it a 0, is it a 4, is it a 1, a 9, and so on. And in order to learn from that, for those that didn't have machine learning courses, usually we need some existing data where people maybe have annotated this already. It's an area called supervised learning, which is, let's say, the best understood, where people have already looked at the image and says, this is a 10, this is a 0, this is a 9, this is a 7, right? And this data is given to you. So now we have to see how we actually look into this data. And there, Python scripts are usually very heavily used to really understanding now how you come from these images basically to a proper data structure. And this is the example of MNIST character recognition. Someone used that maybe already. It's like a very famous example in different, let's say, versions here and there, but in the end, they capture the same essence. And of course, in lecture 6 and 7, we will build on that, and we'll also tell you what's the difference between neural networks using it and also deep learning using it and so forth, starting with a very simple perceptron learning model, the simplest one that you can have, and going much more advanced. But here we are at the start of the basically of the whole projects that we have in the course and also of the environments. So this is something to think about, to really get a feeling for it. Now, when you now use a cloud and you basically use, just wanted to demonstrate that a little bit, you often basically have the situation that you do the following. You have a Jupyter lab maybe, or you go again to Jupyter JC here, and you create a new instance. You can here add a new Jupyter lab if you want, and we use here the HDF cloud for it. As I said, it's a very specific cloud available essentially for data science, but for many other things. And when we start this, you will see it's maybe don't have all the packages you need. So we said now we want to do this number recognition, and we wanted to do it in a very specific way. We do keras and TensorFlow analysis with it. So we need, of course, packages keras. We need maybe TensorFlow to look at it. And now I want to use a cloud. And the interesting thing is, of course, a cloud is never directly configured as you like. So you have to learn about specific tools like pip. Someone has used pip install already? Yeah, okay, it's a famous tool for installing, let's say, for instance, packages that are missing. Also locally, of course, but also in the cloud that works here and there. There, of course, are again hiccups. You have to do this as a -- user often, because you cannot just pip install everything. You don't have the rights for it, right? You have to use it in a certain user space. I just demonstrate this a little bit. I uploaded here already the pre-processing one. And essentially here you see that the keras dataset has this MNIST, which is basically then downloading it and basically making it available in the cloud. But if keras would be not installed right now, we would have an error, right? That would be looking then like I have here on this slide. So essentially, I have prepared that because it would take some time to do pip install. But essentially, in this point in time, when you would execute this, you would find, of course, keras is not there, but it doesn't hinder you in cloud environments. So you can essentially go around this with doing what you see here in many cases. And this is, of course, not specific to keras, right? You can do pip install user TensorFlow, right? Or pip user keras. Just a demo here that you see that I already prepared that a little bit for us would be using the launcher and the terminal. Now we basically are again in the cloud remotely on this kind of command line and could do the same or same pip install. Let's say this is important in the user space, keras, and it will check now and install keras, or it will say, well, it's already installed before, right? But I just did this because of saving times. And you see here requirements already satisfied. Otherwise, it would now take all the packages and install it for you. So wherever you go to the cloud, be not disappointed if it doesn't have the packages you need. Chances are you can pip install it, right? And then create also virtual environments, but this is a topic we'll cover later. Good, but in the end, coming back to our example here a little bit, you see that this was basically executed in this particular script. And here you see now we're using something that we imported from keras from the dataset, which is the MNIST dataset. it is already provided inside the Keras package for convenient, basically access to this, let's say, benchmark or tutorial data. So it will be automatically loaded online and already put in something we call a test and a training data set. That's why you see here this interesting differentiation between training and testing. That is important for machine learning. We will learn about this in lecture 2 next week. So it just shed a little bit light on it, that basically the pixels that you see here is X. You see that this is, of course, a 28 by 28 situation in an image. We said the resolution is 28 by 28 pixels. So we have a matrix really, right? That's why it's in capital also here. And Y usually is a label to it. So that means someone already for us has said, this image is a 7, this image is a 0, this image is a 2, right? We call that a labeled data set for machine learning. And this is important for us because then it enables supervised learning mechanisms, which are very successful. Unsupervised is not always very successful, but also very powerful, but still requires much more work. So still the question is how that really looks like, right? We have no data, we have it nicely downloaded, and we have here a small function just for basically transforming now each of the different, let's say, elements from this matrices and from this, what you have here in the train, for instance, training set, really each individual piece we take here and can basically then print it out in this kind of format, which is nothing else than the grayscale. So that's how the real image come to be, right? So what we've seen before with the 7 and black and things like that. This is nothing else than intensity of grays that you have here. So you see very intense parts here and zeros, of course, where's white. And that's how you do, let's say, data exploration tasks. So you look in the data, use Python briefly for it. We see here, we go a for loop, taking maybe the first 50 out of this. This is now basically all the same idea. But you see essentially when you go a little bit away from the screen that it resembles quite nicely the label, right? You have a 7 almost here that someone has already, let's say, done for us. Of course, the idea of machine learning is now that whenever you paint again an 8 or so, we just throw it to this machine learning system we're going to create, and we will learn what that means in lecture 2 and so on. And to really automatically know that this is a 2 or 8 or a 0 without the label. Right? We talk about unseen data, new data sets. But once I've trained the system, learn from this, it's actually to 99% accurate in finding this. And deep learning is there responsible for it. So what we also will learn then in lecture 6 and 7. So here really the baby steps, still important, what all data scientists are doing, data exploration, how the data really gonna look like. We know it's paintings, but now we know exactly it's 28 by 28 pixels. We have grayscale and things like that, and what the label nature is. And of course, now you would continue with lecture 6, you would use now neural networks and maybe look at this and then switch to deep learning networks. But now, of course, we want to have some, let's say, smaller ramp up of the course. That's why we do some practicals, more logistic regressions, more simple mechanisms in machine learning before we go to more cutting edge deep learning mechanisms in the cloud. And regression is something what we already will start with next week, essentially. Good. Yeah, so much for this. Of course, it goes without saying that this is a test set. You can also do that with a training set, right? And let me go to some slides to show you also the difference. Again, here you see better examples why you not always do the consecutive thing, right? I just code here test of train, and the nature of the data is the same. It just put away in different pieces. And this is something where we will learn about when we do the machine learning introduction actually next week. So usually we have training examples given to you, always basically in X is the kind of pixels, 28 by 28, here's an example. And then the governing label Y would be always your basically idea of the supervised learning approach. Sometimes you don't have that. So you just have the images and you have to recognize and do unsupervised mechanisms to really learn from that what it is. And also there are strong deep learning mechanisms these days. Now, how you do exactly the separation is really a rule of thumb in machine learning. Here and there per use cases, basically you would say take the less as possible for training, but not too little, because you need certain number of trainings to really get the model right. but keep the most as you can for unseen data. We call testing, if possible. In advanced machine learning and in state seminar, you probably have learned about the validation data set, right? Cross-validation. This is even more important. If you're swimming in data, then you throw validation sets in all different corners, the testing set as well, just training on the data. And whenever you pick a parameter, you would pick a validation set and pick the parameter, because then it's contaminated. But these are all things we will talk about in lecture 2, and also to a moderate degree. Of course, then it goes really into deep statistical learning theory of how much data is needed for the capacity of the model you have, so something we call Babnik-Chervonenkes inequality, but which really then more machine learning course material. It essentially means that regression needs less data than a bold deep learning network, right, with 26 million parameters to train. Good. For you on the slide, some explanation of what I have demonstrated so that you can follow that. Maybe towards the end, just a short demo here for association rule mining. That will be lecture 11 for us. It will be all about it. Again, an idea of how you use Python for shopping data, so transaction essentially. The different algorithms around a priori, FP gross, Mafia, they all try to gauge basically what would be the products that people buy together that you can recommend, right? You're at the cashier and you have just buy one, like beer, and you get, basically diapers as a good example, what always is bought together. And we come to an example why that is actually the case very soon. We do this, for instance, ourselves in many different research projects, and it's a really hot topic, especially if you combine online with offline worlds. And now we have iPads at the cashier telling you, yeah, please, when you have bought this, please also buy this. I think you're really highly interested in that. And these algorithms are, for instance, a very good demonstrator of cloud computing, because the transaction data is very similar like the data you said. Sometimes your Excel is not helping there anymore. And if you go to advanced algorithms, like for instance, a priori, it's also not really scaling very much anymore. You really need for big data sets, things like FP gross built more on the tree structure and using parallelization. But this is something, of course, what we do in lecture 11 here. I would just to emphasize on the fact that you can use with a little bit of Python already basically a solution for a shop owner. All you need is a bit transaction data. We do this, for instance, with a perfumery store and this on for off project. That's why I did this example. Of course, with some, let's say, more easier data than you basically know from some, let's say, real shopping. But here's a good example how that works. You essentially try to identify those which are always bought together. And then, of course, if someone has in the shopping basket just the diapers, you can basically recommend then the beer. And there is these algorithms from a priori, FP gross, and so on that actually are identifying those. And if you have, let's say, 30,000 or maybe in the millions of transactions, of course, as a human, you don't really grasp that anymore, right? It's very hard to understand what is bought together, especially if you think about that product A, product B is bought together, and that always means product C. Right? Not always is a one-to-one. It could be a one-to-many or many-to-one dependency, which these algorithms also capture. And there, hence the motivation for cloud computing. If you have many of those, you really need the processing code. You need the memory where computing comes in. And here the algorithms gets incredibly important. When you want to use this for yourself, I will provide the slip. Here's the MLextend library, for instance, another one, which is quite nice. In Python, you just implement this. There's a couple of lines, get basically the rules, the association rules out, and you can use them then for a shopping owner here for the right-hand side, this actionable insights. You can basically change the product portfolio. You can change the store setups. Of course, things which are bought together should be put on the other end of the store so that you take the most time on the shopping area, as it is called. We as customer would say the same inverse. We would say it would be nice to have all of them directly next to each other that are bought together. But of course, the shop owners do exactly the opposite. Also with the PAAS, usually through the snacks area, so that you take some things. If you go to a Belgium, basically supermarket, you see this very nicely. The Belgian beer is always extremely in the back, so that you go through all the supermarket, take all your chips and snacks, and then end up at the beer that you really wanted, instead of having it directly at the cashier. So these are, let's say, the way. And in order to identify those, basically they use these algorithms. And of course, in online, there's even more possible with recommendations. But we come to this in lecture 11. just think about here some small elements of how you would configure this. Essentially, you're talking about support, how many of those are in the baskets and so on. And that's what we will talk about in lecture 11. And the beautiful thing is now when you see that it's basically implemented, and we will learn how the algorithm works then when we have this lecture. But when you come basically to the idea of here we're going local again, just for the sake of time. But here you see the association rule mining example has just a couple of lines, really. Here's the example with Pieper. Pieper is a perfumery. So we're talking here about some, let's say, reduced amount of perfumes altogether. You see, we use a data frame from pandas, Numpy, MLX10 for frequent patterns, which is this a priori algorithm to find the frequent item sets. And based on those, you can make the association rules. We talk about this in lecture 11. Here it's just to realize that just with a little bit, a couple of lines, and of course, some data you need. In all machine learning, you need the data here. You see we have some retail data, which is a fake data set. I've simplified a bit. You see that here in the data. Essentially, it looks like this. Not a big surprise. You would have just, you know, the shopping transactions. So what products are in the shopping basket one by one by one. And we're reusing this data just with a couple of Python code lines and make some inspection here. You see it's really heavily simplified in terms of the names. Usually would have them in different milliliters and so on. Just here, the unique idea. So how many different products are there? That could be interesting for some. And one of the ideas of this algorithms is to use a so-called one-hot encoded. That means we are not really interested in this transactions, comma, 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 but we rather want an overall situation of saying just every time it is bought, we would have a 1, so a very big matrix, which says 1 if it's bought or 0 if it's not bought per transaction. It is a way of basically standardizing for algorithms the data set. It looks a little bit like this. You see, right, in the transaction 0, there was just rituals, Lancome, and no clinic bought. So things like that, basically, you can nicely use this Python. You see it's interactively possible with Jupyter notebooks very nicely. You can influence you directly see the visible outcome, which is also nice. And here you see then now the frequent item sets. And you see apparently clinic is incredibly often in the data set. And as a consequence, you already can imagine a little bit that the association rules will actually point to that. But it must be not the case because there are many different, let's say, configuration options we will tackle in lecture 11 then once you're there, where you have, let's say, to interpret support and confidence, of course, but also with lift and leverage and conviction, you would have different angles, essentially how you interpret the results. But here we would probably go to the highest support when we think about here some of the numbers or in the slides. Here you see the confidence is something what we would see very highly in 0.81. So in other words, when someone is basically using here bioterm, you can basically recommend clinic. Now here in this example, many of those will basically put clinic, but here you can be more confident, let's say, that than in other situations of providing this. And this is what the algorithm just can compute very nicely. The beauty now is to jump to the cloud is that this would scale. And we have to talk about also that not all algorithms are ready for it. A priori, for instance, one example, you have to really do it in a certain fashion to be scalable. Good. So in a way, that's also all on the slides. Just to reiterate on what we had with MNIST, the library. Of course, this is basically the retail data is nothing else than cheese and bread and meat. So you can, of course, have this from different, let's say, areas. Doesn't need to be perfume. And of course, very simplified because normally you would have different milliliters and things like that, which of course also steer shopping behavior. And this motivates then also having the big data, right? So these transactions are very large. You need lots of those. And in the end, of course, you don't want to have thousands of these rules given to the shop owner. So in the end, you basically would take some of these relevant rules, pick 2 or 3, and then recommend to the different customer, right? You don't want to give the customer, well, these are the 1,000 rules you could buy, which means you also have to do some manual tweaks to go to the, let's say, 2 or 3 best ones. But you have seen with such little of Python, you can go now to a shop owner and say, give me your data, I give you recommendations, and maybe get a check for it. So, and this is of course beautiful today. And it works really in practice. We are doing this on a large scale with Pieper with 150 stores in Germany, and there are always very much surprises. So, I mean, some of those rules are known by the gut feeling of the shop owners and of the people selling, especially this product with that product. But until when you go to double tons and triple tons, you don't know what that is, but we will see in lecture 11, things bought together in larger quantities, then it's getting easier. Good, but yeah, so scaling up these millions of baskets, you can imagine the more products you have, 60,000 are alone with Pieper, for instance, where we work with, then of course transactions are in the millions, then your laptop is quickly out of power for this, to do this efficiently. So that's the lecture bibliography just for you again, all of this to look up. If you like, I should also acknowledge my team here. You see my PhD and master students right now. So they also do a hell of a lot of work that I can always present you nicely in the back, or do work on libraries and so on. So I'm incredibly grateful also to those great team